In this presentation, fluid machinery and Pelton turbine experiment, which is the sixth experiment of the machine laboratory, is going to be examined. The purpose of this experiment is to short introduction to the fluid machinery and then understanding of the Pelton turbine's specifications. For example, component of Pelton turbines like buckets, penstock, nozzle, and performance parameters of Pelton turbines. First of all, we can start with energy. What is energy? Energy can be described as it is an ability to do work. People use energy to walk and bicycle, to move cars along roads and boats through water, to cook food on stoves, to make ice in freezers, to light our homes and offices, to manufacture products, and to send astronauts into space. There are many different forms of energy, including kinetic, pressure, potential, strain, thermal, and hydraulic. Hydraulic energy is a type of renewable energy that is powered by the force of fluid. Fluid machinery can be described as it is a device which converts the energy stored by a fluid into mechanical energy or vice versa. Or fluid machinery is used to convert hydraulic energy into mechanical energy or mechanical energy into hydraulic energy. There is a distinction about converting energy between hydraulic energy and mechanical energy because of the direction of energy transfer and different group of fluid machinery. Fluid machinery is divided into two categories, driven machines and driving machines. In driven machines, energy is added to the fluid and it can be described as power-consuming machines, which convert hydraulic energy into the mechanical energy, like turbines, motors. In driving machines, energy is removed from the fluid and it can be described as power-producing machines, doing the reverse like pumps, fans, or compressors. Another classification of fluid machinery is also done based on the motion of moving parts, rotodynamic machines and positive displacement machines. On the right side, the classification of fluid machines can be seen. Turbine, subgroup of rotodynamic machines, is a rotary mechanical device that converts hydraulic energy into the mechanical energy, and it can be classified into two basic types, impulse and reaction turbines. Also, turbines can be classified due to working fluid used, such as gas turbines, steam turbines, water turbines, and wind turbines. While Francis turbines is given as an example of reaction turbine on the right side, and Pelton wheel, which is on one of the most famous turbines, is given as an example on the left side of impulse turbine. The impulse turbines are driven by one or more high-speed jets. The total head of incoming fluid is converting into the kinetic energy with one or more high-speed jets. The fluid strikes to the vanes which are attached on the rotating wheel. Then work is done on the runner, since angular momentum and motion of vanes. Hence, energy is transferred. Since the fluid energy which is reduced on passing through the runner is entirely kinetic, it flows at the absolute velocity at outlet is smaller than the absolute velocity at inlet, jet velocity. Furthermore, the fluid pressure is atmospheric throughout and the relative velocity is constant, except for a slight reduction due to friction. Pelton turbine or Pelton wheel, an impulse turbine, is one of the well-known types of water turbines. The modern and most efficient types of impulse turbine was invented by Lester A. Pelton in 1878. The buckets of a Pelton wheel are designed so as to split the flow in half and turn the flow nearly 180 degrees around with respect to a frame of reference moving with the buckets. One or two nozzles project a jet of water tangentially to the vane pitch circle. The vanes are of double outlet section, as shown in figure, so that the jet is split and leaves symmetrically on both sides of the vane. Components of the Pelton turbines. Runner is a rotating part of the turbine. It is a circular disc on the periphery of which a number of buckets evenly spaced are fixed. The buckets are made by two hemispherical balls joined together. Each bucket has a valve in between two hemispherical balls called splitter. The splitter splits the jet of water, striking the buckets into two equal parts, and the jet of water comes out at the outer edge of the bucket. The buckets are designed in such a way that the jet of water strikes the buckets, deflected through 165 degrees. The buckets of the Pelton turbine casted as single solid piece in order to avoid fatigue failure. Nozzle is used to increase the kinetic energy of water that is going to strike the buckets or vanes attached to the runner. The quantity of water that strikes the buckets is controlled by spear. The spear is installed inside the nozzle and regulates the flow of water that is going to strike on the vanes of the runner. A nozzle containing spear is shown in the figure given right. The spear is a conical needle present in the nozzle. It is operated by a hand wheel or automatically in an axial direction. When the spear is moving backward, the rate of flow of water increases, and when it is pushed forward, the rate of flow of water decreases. The outer covering of this turbine is called casing. The Pelton turbine with the casing is shown in the figure. It prevents the splashing of the water and helps to discharge the water to the trail race. It also acts as a safeguard in the case of an accident occurs. Cast iron or fabricated steel plates are used to make the casting of the Pelton turbine. When the jet of water is completely closed by pushing the spear in the forward direction, then the amount of water striking the runner becomes zero. But still, the runner keeps moving due to the inertia of the runner. In order to stop the runner in the shortest possible time, a small nozzle is provided which directs the jet of the water at the back of the vanes. The jet of water used to stop the runner of the turbine is called braking jet. Governing mechanism. The speed of turbine run is required to be maintained constant so that electric generator can be coupled directly to turbine. Therefore, a device called governor is used to measure and regulate the speed of turbine runner. What is the working principle of Pelton turbine? The working principle of Pelton turbine is as follows. The water is transferred from the high head source through a long conduit called penstock. Nozzle arrangement at the end of penstock helps the water to accelerate and it flows out as a high-speed jet with high velocity and discharge to the casing. The jet will hit the splitter of the buckets, which will distribute the jet into two halves of bucket, and the wheel starts revolving. The kinetic energy of the jet is reduced when it hits the bucket, and also due to spherical shape of buckets, the directed jet will change its direction and takes U-turn and falls into tail race. In general, the inlet angle of jet is in between 1 to 3 degrees. After hitting the buckets of deflected jet angle is, before said, 165 degrees. The water collected in tail race should not submerge the Pelton turbine in any case. To generate more power, two Pelton turbines can be arranged to a single shaft, or two water jets can be directed at a time to a single Pelton turbine. Pelton turbine design is always aimed to extracting maximum power from water jet or maximizing efficiency. Power extraction is maximum when product of impulse force and bucket's velocity is maximum. If Pelton wheel buckets are held stationary, even if there is huge impulsive force, power extraction will be zero. Similarly, if buckets are moving with same speed of jet, water jet will not be able to hit the buckets, which leads to zero impulse force, and again, power extraction will be zero. In short, power extraction is zero, both have zero bucket speed, and when bucket speed is same as jet speed, optimum power extraction happens in between. So, with respect to jet to bucket speed ratio, power extraction will vary with as shown in below. These are the elements of the experiment setup. It can be seen in this figure: control panel, manometer, bulb, flow meter, generator, valve, centrifugal pump, tailstock, nozzle and penstock, case, emergency button, and main switch. On the left side of the experiment setup, it can be the Pelton turbine wheel and the buckets in here, runner in here, spear, this is the spear, and this is the nozzle. First of all, we make sure of the electrical connection, and after that we open the leakage current relay and the fuse. The left one is the leakage current relay and the right one is the fuse, and we turn on the main switch, and the electric power comes to the control panel and the control panel turns on. There are two menus in the control panel: setting menus and control menus. We are not concerned with the options in the setting menus. The part that interests us here is the control menu. We can give the pump, apply load, and save values commands. When we press the pump button, the pump is activated and pumps water from the tank. When we press the apply load button, the load is applied to the shaft to which the turbine is connected and generate electricity with the help of the generator. When we click the save button, it is saved with all the data we get. As it seems, when we move to the bottom part, we can read the values of temperature, speed, torque, turbine voltage, and turbine current. We see a manometer here. The reason why the manometer is in the experimental setup, as it is known, Pelton turbine is preferred in areas with high altitude and low flow rate. Since elevation cannot be created under university conditions, we obtain the altitude with the pressure, or we obtain the head with the pressure value read from the manometer. And in the right side, the bulb we can see here gives light as a result of the electrical energy obtained from this generator connected to the Pelton turbine with a shaft. In the lowest level of the experimental setup, the water tank can be seen. The water tank filled with water passes through the flow meter with the centrifugal pump, and flow rate can be measured with flow meter, and water is continued in the pipe and finally reach the Pelton turbine. You can see the Pelton turbine. the water finally reaches in the Pelton turbine. Before running the experiment, we open the valve at the bottom of the flow meter. The water in the flow meter flows back into the tank, as you can see. When we press the pump button, the centrifugal pump draws the water from the tank and sends the water to the Pelton turbine. Let's press the pump button. You can see the centrifugal pump drops the water. Now the water flows along the pipe and reaches the Pelton turbine. As can be seen, the centrifugal pump sends the water to the turbine. The water started to come out of the nozzle and hit the turbine buckets. However, since its flow rate is low, it cannot turn the turbine yet. With the help of the penstock or adjustment valve behind the nozzle, the flow rate can be increased and the water hits the turbine bucket faster, and so our turbine starts to move when it gets enough impact force. As you can see, turbine is moving. The values on the manometer change depending on the flow rate adjusted by the adjustment valve. When we press the apply load button, electricity is generated by applying a load to the generator and the bulb starts to light. You can see when we press the apply load button, the turbine slows down as the load suffers. To speed up the turbine again, speed up means increasing the flow rate with the adjustment valve behind the nozzle, and bulb starts to glow increasingly. You can see the bulb. The bulb starts to give light. Here, by increasing the flow rate, the speed of the water hitting the Pelton turbine buckets increases further. The shaft to which the turbine is connected begins to rotate faster and the electrical power generated in the increases. More electrical power means more light from the bulbs, and you can see the manometer here. The value of the manometer decreases inversely with the increasing flow rate. Again, you can see the motion of the Pelton turbine's movement. When we increase the flow rate values, the striking of water is increased to the Pelton turbine's buckets, and then shaft rotates faster. By changing the flow rate from the control panel, torque, speed, turbine voltage and turbine current values can be observed with changing flow rate with penstock or adjustment valve. You can see the flow meter. With adjustment of the flow rate, all values, torque, speed, turbine voltage, for example, is changed, and manometer, the value of the manometer is changed. inversely with increasing flow rate. When flow rate is increased, the values of the manometer is decreased. As you can see the image. And then, after the required values are measured and the experiment is completed, we close the load application button. After that, we cut the flow with adjustment penstock. The shaft attached to the generator stops turning and the flow rate drops completely. Then after that, we turn off the pump and ensure that the water in the pipe goes back to the tank completely, you can see, and close the valve. Then we leave the control panel and turn off the main switch. As a last operation, we close all the fuses and finish the experiment. Here, we can change the flow rate by adjusting the spear at the tip of the nozzle. You can see the water flow motion at the tip of the nozzle. With lowering power demand, spear rod is moved into the nozzle. With lowering power demand, spear rod is moved into the nozzle so that water flow rate is reduced. If power demand increases, spear rod is moved out. This will increase flow rate. You can see the spear rod is moved out. The flow rate is increased right now. And then, if we want to lowering power, we should spear rod to move is into the nozzle, and the Pelton turbine is completely stopped. And finally, Pelton turbine is suitable for operating when water energy is available at high head, for example 30 or 50 meters or higher, and low flow rate. Overall efficiency of Pelton turbine is very close to 90%. This is the end of our fluid machinery and Pelton turbine experiments. All the necessary parameters will be given to you to do calculations in the experiment. Please read the laboratory paper carefully. All formulas you need are in this paper. Be careful with the units while doing calculations.